Nucleophilic substitution reactions. In this chapter, we will learn how alkyl halides react with nucleophiles in nucleophilic substitution reactions. We will study the effect of structure and stereochemistry of the alkyl halide and solvent on nucleophilic substitution reactions. We will learn to predict whether nucleophilic substitution reactions occur through an SN2 or an SN1 mechanism. We will study under what conditions alkyl halides undergo elimination reactions instead of substitution. We will study how structure and stereochemistry influence the products formed in elimination reactions. We will learn to predict if an alkyl halide would give substitution or elimination product under particular reaction conditions. Reactions of alkyl halides. Nucleophilic substitution. In alkyl halides, the carbon-halogen bond is polarized due to the higher electronegativity of the halogen. For example, in bromomethane, the CBr bond is polarized, making the carbon electrophilic. The electrophilic carbon in alkyl halides reacts with nucleophiles in nucleophilic substitution reactions. Example, bromomethane reacts with hydroxide ion, a nucleophile, displacing bromine to give methanol. The reactivity order of alkyl halides is influenced by both the length and strength of the C-halogen bond. Alkyl iodides are the most reactive and alkyl fluorides the least reactive. Reactions of alkyl halides. Nucleophilic substitution. The reaction mechanism of all nucleophilic substitution reactions depend on 1. Whether the alkyl halide is a primary, secondary, tertiary, benzylic or allylic halide. 2. Whether the solvent in which the reaction is carried out is a protic or aprotic solvent. 3. Whether the nucleophile is a strong base or weak base and its concentration. The reaction mechanism for the reaction between bromomethane and hydroxide ion has been elucidated by rate studies which determine the effect of concentration of alkyl halide and nucleophile on reaction rate. It was found that doubling the concentration of either the alkyl halide or nucleophile doubled the rate of the reaction. Doubling both quadrupled the rate. The rate is consistent with the rate expression. Rate is equal to K multiplied by the concentration of bromomethane multiplied by the concentration of hydroxide ion, where K is the rate constant. The above rate expression dictates the involvement of both the alkyl halide and the nucleophile in the rate determining step of the transition state for the reaction of bromomethane with hydroxide ion. SN2 mechanism for the reaction of bromomethane with hydroxide ion. A single step or concerted mechanism called SN2, S substitution, N nucleophilic to bimolecular has been put forward for the reaction between bromomethane and hydroxide ion giving methanol. The mechanism involves the participation of both the alkyl halide and the nucleophile in a pentacoordinate transition state. In the transition state structure, the negative charge is shared between OH and Br. From the moment the nucleophile attacks the electrophilic carbon, as the reaction proceeds forward, Br continuously shares a greater degree of negative charge until upon completion of the reaction it becomes Br minus. Inversion of configuration in SN2 reactions. In the reaction between bromomethane and hydroxide ion, the hydroxide ion attacks the carbon from the opposite side, and neither the CO nor the CBr bond breaks until after the completion of the reaction. If the above mechanism were true, then conducting the same reaction on a chiral compound would result in the inversion of configuration. Indeed, when R2-bromobutane is treated with hydroxide ion, it results in S2-butanol due to inversion of configuration. The above reaction provides evidence that the SN2 is a concerted reaction, that is, occurring in a single step without the formation of an intermediate carbocation. Steric effects in SN2 reactions. In SN2 reactions, the carbon bonded to the halogen atom is attacked by the nucleophile from the side remote to the halogen atom. Any factors that can restrict access to this carbon would result in decreased rate of reaction. For example, as we go from bromomethane to bromoethane to bromopropane, the steric crowding around the carbon bonded to the bromine increases. This decreases the rate of the reaction as we go from bromomethane to bromopropane. The fact that as the steric crowding increases on the carbon attached to bromine, the reaction rate decreases provides further evidence for the SN2 mechanism. The effect of leaving group in SN2 reactions. The order of reactivity of alkyl halides is Ri is more reactive than RBr, which is more reactive than RCl, which is much more reactive than RF. We know that the reactivity order of alkyl halides is influenced by both the length and strength of the carbon-halogen bond. Another factor that is even more important is the relative stability of the leaving group. The more stable the leaving group is, the higher the rate of the reaction. The order of stability of alkyl halide anion is I- is more stable than Br-, which is more stable than Cl-, which is more stable than F-. Ri is the most reactive since the leaving group I- is the most stable. Alkyl fluorides are rarely used in nucleophilic substitution reactions since F- is a poor leaving group. The role of nucleophiles in SN2 reactions: good and poor nucleophiles. Nucleophiles can be classified as either good or poor. Good nucleophiles are able to attack the electrophilic carbon more readily, resulting in higher rates of reactions. Generally, good nucleophiles are also strong bases and poor nucleophiles weaker bases, but not always. Nucleophilicity can also be solvent dependent. The role of nucleophiles in SN2 reactions: neutral and charged nucleophiles. Nucleophiles can be further classified as either neutral or negatively charged nucleophiles. The neutral nucleophiles, having lone pairs of electrons, are poorer than charged species. Ammonia and water are two commonly encountered neutral nucleophiles. NH3 is a better nucleophile than H2O. NH3 is also a stronger base than H2O. Most of the commonly encountered charged nucleophiles have one or two electronegative elements that can carry a negative charge. Example, halogen anions below: I-, Br-, Cl-, and F-. Nucleophilicity in protic solvents. The order of nucleophilicity in protic solvents is: I- is more nucleophilic than Br-, which is more nucleophilic than Cl-, which is more nucleophilic than F-. This order of nucleophilicity is surprising, since in this order the weakest base I- is the strongest nucleophile and the strongest base F- is the weakest nucleophile. This order of nucleophilicity in protic solvents like methanol can be explained as follows. I- is poorly solvated since it is less electronegative. Due to its large size, it is very polarizable and able to seek out the electrophilic center with greater ease, hence a good nucleophile. F- is heavily solvated since it is highly electronegative. Its nucleophilicity is considerably weakened due to this. Due to its small size, F- is not very polarizable and hence a poor nucleophile. The small size of the H atom at the positive end of the dipole enables the solvent molecule to access the nucleophile readily and solvate it effectively. Nucleophilicity in protic solvents. Other common nucleophiles have oxygen or sulfur atoms in them. Example, OH-, CH3O-, SH-, CH3S-. Nucleophiles OH- and CH3O- are stronger bases than SH- and CH3S-. However, SH- and CH3S- are better nucleophiles than OH- and CH3O- in protic solvents. In protic solvents, OH- and CH3O- are solvated to much greater degree than SH- and CH3S- making them poorer nucleophiles. Also, the greater polarizability of the SH- and CH3S- make them better nucleophiles in protic solvents. Nucleophilicity in polar aprotic solvents. In protic solvents, the positive end of the dipole of the solvent molecule is able to access the negative nucleophile readily and solvates it effectively due to the small size of the hydrogen atom. In common polar aprotic solvents like dimethyl sulfoxide, dimethyl formamide, and acetonitrile, the positive end of the dipole is unable to approach the nucleophile for effective solvation due to the shape of these molecules. Hence, nucleophilicity of nucleophiles remain undiminished in polar aprotic solvents. The order of nucleophilicity of halogen anions are the reverse of that in protic solvents. Nucleophilicity in polar aprotic solvents is I- is less nucleophilic than Br-, which is less nucleophilic than Cl-, which is less nucleophilic than F-. Similarly, OH- and CH3O- are better nucleophiles than SH- and CH3S- in polar aprotic solvents.